changing the relative position of each monochromator, and you get light out. Okay, so and you have two devices, right, in front and after. The first devices measure I naught. The second devices measure I that pass through, and you insert your sample in the middle. Okay, it's a very simple thing, and it could be just how do you measure photon intensity? Well, it could be just anything that, because a photon, when you pass through some material, it will excite, it will emit photoelectron, right? Because anything is just thin foil. You just, all you need to do is just stick a little thin foil in there and measure the electron that emit out, and then you collect the electron that come out. So you can, as simple as just measure the photoelectron current that pass through a thin foil. So you have one that go through and another thin foil at the back, and you measure the current, and that current should be proportional to the X-ray intensity, because the more the X-ray you have, the more photocurrent that it comes out. Okay, so it could be, it's quite easily done. But the problem, of course, as I mentioned, alluded to earlier in XF, is that your measurement has to be so good. Remember, these little wiggles are under 5%. You cannot have a lot of noise in your measurement. And these experiments are usually extended over a period of 2 to 5 hours. Literally, you have to make sure that your measurement is stable to that time, down to 5%, which is not so easy to done. So sensitive electronics is what you need. Okay. So what you got is that the principle of X-ray absorption spectroscopy, I say, is the same. So we just talked a little bit about that. And then you have X-ray absorption and Core excitation. To this, I'll talk a little bit about this later. So you got two regions. Okay, so what you have, discrete excitation lead to peak in absorption region. So you have region that called the causal region. So this is my absorption ionization edge, right? Photon energy at the back. Within the 50 eV is called the causal region. And this is region where you have something called the X-ray absorption Ni-edge structure. SANES, when you hear people call SANES, X-A-N-E-S, N-E-S is the key word. Ni-edge structure, right? Ni-edge structure, which is less than 50 volt from above the ionization edge. You have all these peak. These are peak due to excitation, essentially due to excitation near the ionization edge. So they got multiple excitation processes, right? The funny stuff that happen right after excitation. And that's relatively difficult to understand. And there are a lot of people working in this region, in this so-called SANE region, trying to use the same spectra to tell you not just the electronic information, but structural information as well. But above 50 eV is called the chronic region. Chronic region is where people do XF. So you have extended X-ray absorption structure. So this is where you see this little wiggle between, less than 1% most of the time. If you are lucky, you get 5%. Okay? So this is the region where we are interested when you're talking about XF phenomena. And the difference between SANES and XF is really just the energy, in the energy of the electron wave. So the angular distribution of scattered electron become broadened, right? Because you are talking about slow moving kinetic energy now, electrons that are coming out in the same region. And these electron waves, right, because they're slow, what will happen? Whenever you're dealing with slow moving electron wave, they will bounce around. And when they bounce around, in the physics jargon, they undergo multiple scattering effects. They just not scatter once, they scatter many times before they get out of your system. Whereas in XF, the energy of the outgoing wave is high, about 50 eV, and so they just bounce once with your material, the atom inside your material, and then out of your material. Okay, so So when you're doing XAP, it's better because for structural determination, because you don't have contamination with multiple scattering. Because each time it bonds, right? Because each time it bonds with another atom in the system, you need to know how much intensity you get lost by this bouncing around. And it's very complicated because you don't really know how much you lost when after each collision, the wave interacting with this. If you bounce in one bounce, that's very easy because now you have simple theory to deal with this. And this simple theory is called single scattering analysis, single scattering theory. So basically it means that the Fourier electron may bounce once of the neighbor, and then it's out, and then it's out. Okay? So here we have, in this single scattering theory of XAP, which have been used extensively for reason that, because it's a simple, very simple theory that people can understand, particular material chemists can understand. You don't need to do a lot of complicated scattering calculation to get to where you want. The physicists like to do that, but for material people, they don't care. They just want some answer about the information they are after. And how does it work? So you take what you got, this curve, right? This blue curve, green curve that you got. What they do is that they try to filter out the wiggles. And the way to do that is that they fit a little background to it. So this is the background that I try to draw like this. So arbitrary background, somewhat arbitrary. They try to put the background in between the wiggles, up and down, right? And this little background is mu naught. This is the cross section of the mu naught. So mu naught 1 plus chi. This chi corresponds to the wiggle curves that you got. Okay. So the interpretation from physics is that this mu naught is atomic-like absorption structure because remember in XAP we are talking about deep core ionization. You're usually ionizing the s electron way down, the lowest energy level, the electron in the lowest energy level. Usually you're doing those kind of work. So they are atomic-like because there will be very few interactions, even though there is a chemical shift effect, but they are essentially atoms. So it's quite easy to calculate because people know how to calculate the atomic cross section of the interaction of photon with a single atom. That's quite easily done. Okay, and that can be used to give you this little background, this mu naught here. Okay, and the auxiliary part is the XAP modulation part caused by interference effect. Can then be written like this. So this is basically filter out. After I take out my background, atomic background, I got this wiggles. Okay? And so let's look at, in most cases, people compare ionization of an S state. So you ionize a S electron, right? And in jargon of X-ray absorption spectroscopy, this is called the KH. We'll come to that later. And then we'll look at Horn scattering. And what we can show from this theory, you don't need to, I just want to give you a flavor of this. You can show the chi curve can be written in two parts. One is the amplitude part, and then you have a sign which describes the wiggles, right? And there's the phase information in here. Okay? And so that's basically it. So you have amplitude and you have angles, essentially the phase inside your auxiliary structure, which is like a sine curve that you got. Okay? So what you have then is that you got E naught is the energy of the ionization in here. So this is the amount of photon energy above the ionization edge. So if I look at a typical one, this is my ionization edge somewhere in here. So anything above it, right, will be photon. This is my photon, h mu here. Right, h mu minus this E naught. So E naught is here. Like that. Okay, so I'm looking at my different energy. And of course, what is that different energy tell me? That it tell me the kinetic energy of the electron waves that I need to consider for the interference effect that I have. So what you're looking for then is that you fit this background, you cut out